To illustrate the the Poisson distribution, I'm going to look at the example here on slide 34 of the chapter 14 notes on discrete random variables. We are told here that we have a pump in a cannery has a failure on average once in every 5,000 hours of operation. Now, the reason this would be a Poisson distribution, or we could use the binomial, but one of the reasons why it's a Poisson is because we're given the average number of failures over a particular time period. In this case, it's 5,000 hours of operation. When you use the Poisson distribution, you need to know the average or the expected or the mean number of times something is happening. And in this case, as we have here, the mean is equal to 1, the expected value or the lambda value. Now, in part A of the question, we are asked to find the probability of exactly 2 failures. That's simply going to be find a probability x is equal to 2, given that the expected value is 1 in the 5,000 hours of operation. In part B of the question, we want more than 1, so 2 or more. But in question B, the time frame has changed. We are looking for number of failures over 1,000 hours of operation, not the 5,000. This means we need to make an adjustment to the expected value, which I have here and is shown on your next slide. So we know that there's 1 failure expected in 5,000 hours. So how many failures are expected in 1,000 hours? That's going to work out to 0.2. which would make sense because it's 1/5 the time frame. In part C of the problem, find the probability that no failure will occur in 10,000 hours of operation. 10,000 is twice the 5,000, so if I bring this in here, we know the expected is 1 in 5,000 hours. If the time frame is 10,000 hours, then we expect 2 failures. Okay, so going to Minitab, and hang on one second. In the first part of the problem, first of all, we're going to the calc probability distributions, and we want to use the Poisson distribution. In the first part of the problem, we know that the mean, or the expected number of failures in 5,000 hours, is 1. And we were asked to find the probability that x is precisely equal to 2. So change your radio button to probability, input your constant, which is 2, click OK, and there's the answer, which shows in your notes. In the second part of the question, or part B of the question, the expected number has gone from 1 in 5,000 to 0.2 in 1,000 hours of operation. We were also asked to find the probability of more than 1. So more than 1 is find the probability of 2 or more. Now, as we did in the binomial distribution, we know that the total probability over all values of x has to equal 1. And we are going to subtract from that the probability of the numbers we do not want. And we don't want the probability of 1 or the probability of 0. So change your radio button to cumulative probability. Click OK. Here I've got cumulative distribution. And keep in mind this says less than or equal to. As shown in your notes, the way to get the answer will be to take the number 1 and subtract this probability from it. What will remain will be probability of 2 or more. In the last part of this question, part C, we're asked to find the probability of no failures over 10,000 hours of operation. And over 10,000, we're going to expect 2 pump failures, so mean changes to 2. And I could use either probability or cumulative probability in answering this question because the question asks us to find a probability of no failures. If I use cumulative probability, note my answer is 0.135, but if I go back in here, I could also use equal to probability, and the answer is the same because, of course, there are no numbers less than 0.